I pulled up the calendar so we can all check in and see where we're at before we start our lessons. We're on class number 2. I assigned the trucks project last class. I'll talk about that in a minute. We're going to talk about average and instantaneous velocity today. Your first questions of the day and homework assignment are due today. If you have them, just stick them in the folder that's on your table. Again, you can hand those things in up to a week late with no penalty, but hopefully you have them today. Any questions before we get started? All right. So today in this class, we're going to calculate instantaneous velocities and we're going to connect them to tangent lines. Let's talk about the projects for a little bit. Over the course of the semester, you're going to complete 3 projects plus 1 small project where you reflect on the semester. The first project was handed out in our first class. So you've got your first project, and it's due in about 3 weeks. You can look at the syllabus calendar for the exact due date. All of the projects involve doing problems that are much more involved than a typical homework problem. You'll have to do some reading for several of these projects. With all projects, you're encouraged to work with other students in the class. Talking about calculus with a classmate is one of the best ways that you can learn calculus. Since the projects are so involved, it's highly recommended that you try to stick to the timeline that is attached to the front of it. Don't wait until the last minute to try to do the projects. There's a reason you have 3 weeks and not 3 days. An upcoming class period, which is in the calendar, will be devoted to checking in with each other and me on your projects. Okay, so you want to come to that class with as much done as possible so that you can compare and discuss with your classmates. You'll get the most out of that if you've been keeping up with the suggested timeline. Questions on the projects? Okay. I'm going to have you jump to the group activities on the next page, and we'll come back and do the demo in 10-15 minutes. All right, so suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto. That's 450 meters above the ground. We're going to estimate the instantaneous velocity of the ball at t equals 5 seconds. So I asked you in the activity to come up with an estimate for instantaneous velocity of the zombies. So we're going to come up with a strategy for how to find instantaneous velocity in a different context here. Then you can apply it to the zombies after. Okay, so here's a fact. The height s of a falling object is given by s of t is equal to 1/2 at squared plus v naught t plus s naught. A is the acceleration due to gravity, v naught is your initial velocity, s naught is your initial height. So for our ball that we're dropping, what is the acceleration due to gravity in meters per second squared? Negative 9.8. So half of that would be negative 4.9 t squared. What's the initial, if you're just holding a ball off the edge of the tower and you let go of it, what's its initial velocity? 0, yeah. So plus 0t plus s naught, which is the initial height, 450. All right, so I want to estimate how fast it's traveling at exactly 5 seconds. Okay, so I can come up with an average speed, right, over the first 5 seconds. How would I do that? I want to know over the first 5 seconds, on average, how fast was it falling? Yeah, yeah, so average speed, the average velocity is change in distance, which is s in this case. We'll call it change in height divided by change in time. Right. So I'm going to grab a calculator to help me do these calculations quickly. So my function is negative 4.9. I'll use x because I don't have a t. Negative 4.9 x squared plus 450. I'm just going to look at my table, which lets me pick x values, and I'm going to put in 5 and 0, right? So 327.5 divided minus 450. Those are my two heights, right? So I can find my change in height by subtracting them. At 5 seconds, it was 327.5 meters off the ground. At 0 seconds, it was 450 meters off the ground. Over a change in time that was 5 seconds. Divided by 5. So I get negative 24.5 meters per second. That is the height of the ball after 5 seconds. Oh, so you just plug 5 in. I just plugged 5 into my formula. Yep. All right, so a couple of questions. First, why is that number negative? The ball is falling. Perfect. Very good. All right, second question. Is this number, which is the average speed of the ball over the first 5 seconds, is that a very good estimate of the actual speed at 5 seconds? No, because when things that are falling accelerate, right? So it started at 0 meters per second and it finished faster, right? It speeds up the whole time it's falling. So that's its average speed from 0 seconds to 5 seconds. How could I get a better estimate if I wanted to know how fast it's moving at 5 seconds? Average 2 points that are closer, yeah. I could draw a tangent, but that's pretty inaccurate at this point. 2 points that are close? Yeah, 2 points that are really, really close together. All right, so let's say 4.9 seconds to 5.1 seconds, I could get my average velocity. So I'm going to do another average velocity calculation. Change in s divided by change in time, right? And this time, I'm going to do s of 5.1 minus s of 4.9, right? That's going to be my change in height over that interval. And then my change in time would be 0.2, right? 0.2 of a second from 4.9 to 5.1 seconds. All right, so now I'm going to have my calculator do all of this. My calculator knows function notation. So I'm just going to type in basically exactly what I have up here. I'm going to have, I have to use y. So bars, y bars, function y1 of 5.1 minus bars, y bars, function y1 of 4.9 divided by 0.2. Negative 49 meters per second. A much better estimate. Much better estimate. What if I wanted to be even more accurate? What would I do? Make the interval smaller. And I would just keep making the interval smaller and smaller and smaller, and I would get more and more and more accurate. All right, so let's look at what this looks like graphically as we make this interval smaller and smaller and smaller. So I've heard the word tangent line come up here a couple of times, but I purposefully haven't said it. So this purple parabola, that is the ball, right, that we're dropping off the CN tower. See, it's got an initial height of 450, and then it falls, right? It's approaching a height of 0 over about 9.5 seconds. All right, so this blue line is called a secant line. It goes through a line that goes through 2 points on a curve is called a secant line. And I'm interested in the speed at 5 seconds. Okay, so the slope of this line, of this blue line, tells me the velocity, because the slope of a line is rise over run, right? Right, so slope is rise over run. And in this case, rise is distance, right? is a change in distance, and run is a change in time, so that's a velocity. Okay, so the slope of a secant line is actually calculating average velocity. So as I take this point that's varying and move it closer to the point that I'm interested in, I get a smaller and smaller time interval that I can calculate velocity over, right? Until I actually touch it. And then the kind of line that I've created is called a tangent line, right? It does. Yep. We can do it from the other side too. We could calculate average velocity from, say, this looks like it's at 1 second to 5 seconds, and then move this point closer. Then calculate average velocity 2 seconds to 5 seconds, 3 seconds to 5 seconds, 4 to 5 seconds, 4.5 to 5 seconds. And the smaller the interval, the closer we're getting to an instantaneous velocity. And graphically, the closer we're getting to a tangent line, where instead of that line going through 2 points on the curve, it just touches at the 1 point that we're interested in, and the slope of the tangent line is the instantaneous velocity. Of course. The one at 5? It was the question. I asked, I was interested in the instantaneous velocity of the ball at 5 seconds, right? So that's why I picked that one. Okay, and it looks like my slope does approach -49. So that does look like a good estimate. As this varying point gets closer to the fixed point, it's approaching -49, which was our estimate doing some algebra.
What's the variable A?
Oh, A is the acceleration due to gravity. So in this case, it was -9.8. Yeah. Okay, so a good definition. A secant line is a line that goes through 2 points on a curve. A poor definition. A tangent line is a line that goes through 1 point on a curve. It's kind of a poor definition because if this is my point I'm interested in and I draw a tangent line, right, it just touches that 1 point. It could cross the curve somewhere else, right, but it's still a tangent. Right? So it goes through 1 point on a curve, and that's what makes it a tangent. Okay, so the graphical interpretation of average velocity was the slope of a secant line. Right, because average velocity is change in distance over change in time. So on the curve, you pick 2 points. When you calculate change in distance over change in time, you're actually calculating the slope of the line that connects those 2 points. But instantaneous velocity, if we want instantaneous velocity, we move those 2 points closer and closer and closer and closer to each other to get a better and better estimate of instantaneous velocity. And then once one lies right on top of the other, what you have is a tangent line. So instantaneous velocity is the slope of a tangent line. All right, what do you think? Any questions? All right, so you can either pick up where you left off with the zombies. If you completed the zombies, move on to the next page after the zombie questions. And we're going to save 10 minutes at the end for one more demo with the board. Okay, so here's some important stuff, hopefully, that you got out of your activities. The instantaneous velocity of a function, y equals f of t, at some time t equals a, v sub instant, right? We find by taking the average velocity from a to a plus h, where h just represents some distance to the right of the point you're interested in, right? And then we take the limit as h goes to 0, right? And so h representing the change in time, as the change in time goes to 0, as we make that time interval smaller and smaller and smaller, we approach the instantaneous velocity. So this fraction, f of a plus h minus f of a all over h, which represents average velocity over some time interval h, is called the difference quotient of the function f. So in your homework, they might ask you to calculate difference quotients. That's what that is. When we talk about the slope of a curve, we actually mean the slope of a tangent line to that curve. So what does the slope of a tangent line represent? Instantaneous velocity. Yeah, today we're only looking at distance time graphs. Okay, so here's a problem from your reading, right? Suppose Ian throws a grapefruit straight up with an initial velocity of 100 feet per second from a height of 6 feet. Without a calculator, we want to find the velocity of the grapefruit 1 second into its flight. So we're going to do kind of a long calculation. We're going to use the difference quotient. We're going to take a limit. We're going to find the instantaneous velocity after 1 second. So the first thing I need to do is come up with an accurate S of t here. The height of the grapefruit at time t. So remember, we have this 1/2 at squared plus v naught t plus s naught physics formula. And a is, we're dealing with feet here this time. So a is negative 32, the acceleration due to gravity in feet per second squared. So I'm going to have negative 16 t squared plus v naught t. In this case, v naught is 100 feet per second, plus s naught, which is 6, the initial height. So I replaced the a with a negative 32. Yeah. So the 1/2 of that is negative 16. All right, so now I'm going to use this new thing I've invented, right, that we came up with today. The instantaneous velocity of any object, it can be found by taking this limit. The limit as h goes to 0 of f of a plus h minus f of a all over h. H is representing our time interval, our change in time, and a is the time, the specific time we're interested in, which in this case is 1 second into its fall. Okay, so I'm just going to write this down. I want the limit as h approaches 0 of s of 1 plus h minus s of 1 all over h. This is what I'm going to calculate. This will tell me the instantaneous speed of the grapefruit at time t equals 1 second. Okay. So don't forget to copy down your limit as h approaches 0 at every step. We'll take the limit at the very, very end. Right? Save that for the very, very end. For now, I'm just going to try to simplify this difference quotient. It's in the question. The question said, let's find the velocity at 1 second into its flight.
Oh, it says here that a equals like 8 or...
Oh, sorry, there's 2 a's. Yeah, I have a representing the gravitational acceleration due to gravity, and then also I have an a up in this formula. Okay. Yeah, sorry, that was confusing. Okay, so s of 1 plus h. This is just a function notation thing. This just says go up to your s formula, replace all your t's with 1 plus h's, right? Everybody remembers this from like an algebra class? Okay, so I'm going to have negative 16 times 1 plus h squared plus 100 times 1 plus h plus 6 minus s of 1, right? What do you get if you put a 1 into the formula for s? 90. So I'll just put a 90 there. And that's all over h. So that's okay. I'm just going to label what I did here. This, oops, didn't quite go far enough. This is S of 1 plus h. This is S of 1. Okay, so now I'm just going to do some algebra. I'm going to square that 1 plus h. I'm going to distribute my 100. I'm going to combine some like terms. You might take several lines to do this. I don't know how long it's going to take me here. Let's see, negative 16. Square that, I get 1 plus 2h plus h squared plus 100 plus 100h plus 6 minus 90 all over h. $90 is S of 1. Yeah, it came from the S of 1 in the original formula. I just FOILed the 1 plus h. I distributed the 100. Yep. So again, you can write out as much of the algebra as you need to or not. I would encourage you to write it all out because you will make a mistake and you will get frustrated. So just write out all the steps of your algebra here. Okay, so this is, I'm going to combine all my like terms as I distribute this negative 16. So I've got negative 16 plus 100, which is 84, plus 6 is 90, minus 90 is 0, right? So all my constants go away. Then I'm going to have negative 32h plus 100h is 68h. And then I have minus 16h squared. So I distributed that negative 16 and combined like terms all in one step. You might want to write out the two separate steps later when you're doing this on your own. All right, what do you notice about the numerator? Can you simplify that difference quotient any further? Take an h out of the numerator, yeah. So if I take an h out, that leaves me with 68 minus 16h all over h. And h over h cancels. Okay, almost done. This is now the limit as h goes to 0 of 68 minus 16h. So what I'm interested in is what happens to the value of 68 minus 16h as h gets really, really, really small. What is it going to approach? 68, yeah. Because as the h gets really small, the 16h term is going to get really, 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 really small. And this whole thing is going to approach 68. So that's going to be feet per second. That is the instantaneous velocity at t equals 1. We'll do some more of those together. I think there might be 1 or 2 of them in your homework where you have to like actually write everything out and calculate a limit. All right, sorry I went over just a bit.